Welcome everyone. So today we're going to continue more on Taylor series, what we learned so far. Recall that. We said, suppose you have a function, and that function can be written as Tn of x, which is your nth degree Taylor polynomial, plus a remainder, another quantity, if the limit of your remainder while n goes to infinity is equal to 0. Remember that we are just focusing on the interval that we have, or if the limit goes to 0, for sure you can say that, then we can say that f of x is equal to the sum of the Taylor series. So to use this theorem, remember that we use Taylor's inequality. Taylor's inequality, which says, hey, your Rn of x can be bounded by m over n plus 1 factorial, absolute value of x minus a to the power n plus 1 on the interval x minus a less than equals to d. D is just a positive number if the higher derivatives of your function is less than equals to that bound or that constant or that number. So if the higher derivative is less than equals to n, it means that we can bound our remainder by this quantity, then take the limit. If the limit goes to 0, we have this conclusion. Very well. Last time we talked about e to the x. Today we're going to learn how to approximate different functions using our Taylor's polynomial. So this is our goal, to approximate functions using n degree Taylor's polynomial. Okay, what do I mean by that? The nth degree Taylor's polynomial. Remember, we say that, hey, Taylor's series is defined as C sub n, and here you have x minus a to power n starts from 0, goes to infinity, or you can write it in expanded form, C sub 0, C sub 1, x minus a, C sub 2, x minus a squared, plus the rest of the terms, and C sub n's, or these coefficients, C sub 0, C sub 1, C sub 2, can be found using the derivatives of the function at the center divided by n factorial. Yeah, remember that we have the interval of convergence. Perfect. If n is equal to 1, it means that you're just working with the first two terms. T sub 1 of x is equal to C sub 0 plus C sub 1 x minus a, which is just a linear expression. So our function can be approximated by this linear expression. T1x, which is C sub 0, C sub 1, x minus a. This is approximation. If n is equal to 2, let's see what we have. T sub 2, we have T sub 1, now we're working with T sub 2. The second degree Taylor's polynomial. C sub 0 plus C sub 1, x minus a plus C sub 2, x minus a squared. So our function have a better approximation. F of x can be approximated by t sub 2 of x, which is a quadratic expression. C sub 0, C sub 1, x minus a, C sub 2, x minus a squared, which is a quadratic expression. We can continue this process. N equals to 3, it means that we can approximate our function with cubic polynomials. N equals to 4, N equals to 5, and so on. So instead of analyzing our function, we can analyze the Taylor's expansion for that function, which is much easier to work with. We can take the derivatives, we can take the integrals, finding the rate of change, and analyze that function using some nice polynomials. Let's take a look at one example, the example that we saw before, e to the x. Let f of x be equals to e to the x. The standard is equal to 0, and our goal is to analyze e to the x using Taylor's polynomial. So let us analyze this function using Taylor's polynomials. Okay, we saw this guy before. We know that it satisfies all the conditions for our theorem, and we can actually just start writing the Taylor's expansion for this. This function satisfies all conditions. So Tn of x, we saw this before, is C sub 0, C sub 1, x to the n, C sub 2, x squared plus the rest of the terms. Okay, here you have C sub 0, which was equal to C sub n plus the nth derivative of the function at the center divided by n factorial. So C sub 0 is the zeroth derivative of the function, which is e to the x, e to 0 divided by 0 factorial, or just 1. Then we learned about C sub 1, how to calculate that. The first derivative of the function, e to the x at 0, e to the 0 divided by 1 factorial, which is again 1. C sub 2, we calculate that. Again, we have the derivative of e to the x, which is e to the x, e to 0 divided by 2 factorial, a half, and so on. So here your Tn of x is 1 plus 1 x to the first power, and here you have a half x squared, then you have 1 over 3 factorial, which is 6 x cubed plus the rest of the terms. What about our Taylor's polynomial? If n is equal to 1, our function, which is e to the x, can be approximated by 1 plus x, which is a line. N is equal to 2, e to the x can be approximated by 1 plus x squared divided by 2, a quadratic polynomial. If n is equal to 3, e to the x can be approximated by 1 plus x squared over 2 plus x cubed over 6. a polynomial of degree 3, and so on. We can just plug in n equals to 4. You get 1 plus x plus a half x squared plus a 6x cubed and 1 over 24 x to the 4th and the rest of the terms for different n values. Okay, so why we are doing this? Sometimes it's very hard to approximate your function, analyze your function. What are we going to do? We're going to try to check to see if that function has Taylor's expansion, so we can actually, instead of working with that function, work with some nice polynomials that we already know about the properties, how to take the derivative, how to take the integral, and how to analyze these polynomials instead of analyzing the function itself locally. Well, let's take a look at the graph. You're saying that, hey, we want to approximate this function using some polynomials. Well, you all know how to graph e to the x when a is equal to 0. So remember that your center is equal to 0. It means that your y value is equal to 1. So the point that you're actually working with is 0 and 1. So here you have e to the x-axis. Here you have your y-axis. And this is your function, e to the x. Let me use the same color here, 0 and 1. And this is your e to the x. This is our function, f of x. Now let us take a look at these different functions that we have. The first polynomial is 1 plus x. 1 plus x. Let me use green for 1 plus x. This is just a line. So if you have -1 here, if you plug in 1, you get 2. This is your line. One plus x. Okay, so around 0.1, it's not that bad, but if you get further away, the approximation is not very good. You see the difference between these y values. So if I use this quadratic expression, 1 plus x squared over 2, and try to graph this. So this quadratic expression, quadratic polynomial passes through 0 and 1. Okay, but if you want to graph this, the graph is going to be, so let's see if I graph this here. It's going to be this way. So again, at 0 and 1, they have intersection 1 plus x divided by 2. But as you move to the left, to the right, the difference between y values are getting higher and higher. Now, what if I use the last expression? The last polynomial, 1 plus x squared over 2 plus x cubed over 6. I have a cubic expression. So if you look at this cubic expression, the behavior is similar to this. And as you can see, it's better than your line and your quadratic or parabola as the graph of your quadratic expression. So 1 plus x squared over 2 plus x cubed over 6 is better than the line and your quadratic function here. So we're interested in increasing n and getting better approximations, better polynomials to approximate the function. Can take a look at our note for better graph. So this is the graph of e to the x. Then you have your line. Then you have your quadratic. And then you have your cubic graphs. So between these three, T1, T2, T3, T3 is closest to e to the x, comparing to the rest of them. So next example, we're going to work with a function that is actually has a center, non-zero center. Example. Approximate the function f of x equals to the third root of x when a is equal to 8. Using a Taylor's polynomial of degree 2. Okay, perfect. So let's analyze this function. Our theorem says your function f of x can be written as the sum of the Taylor series plus the remainder if the limit of your remainder while n goes to 0 to infinity is equal to 0 on the given interval, the interval of convergence, after finding that. Then if this condition is met, we can say that then the function f of x is equal to the sum of Taylor series. And to find the limit of Rn, we're using Taylor's inequality. It says, hey, if the higher derivative of the function is less than equals to n, or the interval x minus a less than equals to d, d is just a positive number, then if this condition is met, you can actually find upper bound, lower bound for your remainder. So R on n of x is less than or equals to n divided by n plus 1 factorial x minus a to n plus 1. By using Taylor's inequality, we can then take the limit of Rn. If the limit goes to 0, we say that f of x is actually equal to the sum of Taylor series. Okay, perfect. Let's check to see how we can find the upper bound, lower bound for Rn of x. So you might say that, hey, this is my f of x, the third root of x, x raised to a third. What's the first derivative of this function? The first derivative of this function is equal to a third, x raised to negative 2/3, or 1/3, the third root of x squared. Then you can take the second derivative of the function, the third, the fourth, and continue finding the upper bound by analyzing this function. You get negative 2/9, x to negative 5/3, or negative 2/9, x, the third root of x squared. Okay, perfect. And you can continue this process. So let's take a look at our second derivative. How do you find, for example, the upper bound for the second derivative of the function? What is this m? Well, what do we know? We know that we have the interval x minus a less than equals to d. We know x minus a is less than equals to d. D is just a positive number. What is a? A is 8. So x minus 8 is in between negative d to d. This is pure algebra. So your x is in between 8 minus d and 8 plus d. My x is bounded between two numbers. Let's call this L. Let's call this M. Your x is bounded between L and M. Now you're trying to find the bound for this expression. How do we find bound for this expression? This is a quantity. It's just algebraic quantity. How do we find lower bound and upper bound? Well, we start by x in between L and M. Since x is in between L and M, if you flip it, you get 1 over x between 1 over M, 1 over L. Everything is raised to the exponent 5 times. So let us raise everything to 5 over 3. Perfect. So what do we get? We get 1 over x raised to 5 thirds, which is equal to x times the third root of x squared less than equals to this number. This is just a number. 1 over m times the third root of m squared. Again, guys, m and l are numbers. Less than equals to 1 over l times the third root of x. Okay. Now, what if I multiply them by negative 2 over 9? Multiplying everything by a negative number, you have to switch the lower bound and upper bound. So what do we get? We get negative 2 over 9. Negative 2 over 9. And here, this side goes to the left-hand side, negative 2 over 9, 1 over L, the third root of L squared, negative 2 over 9, M, the third root of M squared. Pure algebra. So what do we have here? Do we have an upper bound and lower bound for this expression? This is the derivative. This is the second derivative. I'm just showing you one example how to analyze the derivatives of the function. Your x is bounded between two numbers. It results in the second derivative, in this case, bounded between two numbers. X, 8 minus d, d is a positive number, x plus d is a positive number. Okay, so what is this? This is just a number. Negative 2 divided by 9 times a number on the denominator. Do we have m? Can you say that the second derivative has upper bound, has a lower bound? Is it actually bounded? Can we do that? Perfect. So we just, in one instance, analyze the second derivative, and if you continue taking the derivatives, your denominator is getting larger and larger. And for sure, you can say that, hey, they have upper bound and lower bound for the higher derivative of the function, it means that we can bound the remainder by m, that number, that boundary, divided by n plus 1 factorial times x minus 8 to n plus 1. So Rn of x is bounded by m divided by n plus 1 factorial x minus 8 to power n plus 1. And while we take the limit of Rn, while n goes to infinity, is equal to, take a look at this. Here you have a number times a power expression. A number times a power expression. On the denominator, you have factorial. Factorial goes to infinity very fast. Since your denominator is already at infinity, you have a quantity divided by infinity, which is 0. So our limit goes to 0. It means that our function is equal to the sum of its Taylor series. Okay, perfect. Now let us get back to our question. Our question says, hey, approximate the function by Taylor's polynomial of degree 2. F of x can be approximated by T2 of x. Again, remember that Tn of x is c sub 0 plus c sub 1 x minus a plus c sub 2 x minus a squared plus the rest of the terms. N is equal to 2, so f of x, or the third root of x, can be approximated by c sub 0 plus c sub 1 x minus 8 plus c sub 2 x minus 8 squared. Now we need to find c sub 0, c sub 1, and c sub 2. C sub 0 is equal to the 0th derivative of your function, which is your function at 8 divided by 0 factorial, or 2 over 1, or just 2. C sub 1 is equal to the first derivative of your function, which is negative. So just a third, positive a third, and x raised to negative 2/3 divided by 1 factorial. We plug in 8, we get 1 divided by 3 times the third root of 64, which is 4, so you get 12. 1 over 12. And c sub 2 is equal to the derivative of the first derivative or the second derivative of the function, which gives you negative 2 over 9. And here you have x raised to negative 5 over 3 divided by 2 factorial. Our x is equal to a, which is 8. So here we have negative 1 divided by 9 times 8. Square root of 60. I'm sorry, the third root of 60. Okay. If I'm not mistaken, this is negative 1 over 288. We have all the coefficients. We can actually approximate our function. So the third root of x can be approximated by 2 plus 1 over 12 x minus 8 minus 1 over 288 times x minus 8 to the second power. So we're approximating a cubic function, the third root of x, by a quadratic polynomial. Isn't that interesting? The third root of x can be approximated by this polynomial of degree 2, which we all know is just a quadratic polynomial. Now let's take a look at Desmos. So first function is x raised to a third. So this is our function. Now, take a look at the board. We can just use the first two terms and say that, hey, I want to approximate this function by a linear expression. Let's see. 2 plus 1 over 12, x minus 8. One over 12, x minus 8. You get a line, a linear expression. So take a look at this. Your center is 8. Your center is 8, and at 8, your function is equal to 2. So around this point, on the horizontal axis, you have your interval of convergence around 8. 8 is the center. So we are shifting from 0 to 8. So on the horizontal axis, here you have your interval of convergence, and the point 8 and 2 is here. So if you just use the first two terms, t of 1, you get a linear expression or a line to approximate this function. Now let us add more terms. 1 over 12, x minus 8, and minus 1 over 288, x minus 8. What happened? Okay. X minus 8 power 2. So as you can see, you get a better approximation. This quadratic expression actually is a better approximation than the linear expression. More accurate.